Welcome to CSAI Think Tinker Learn. Today, we're pulling apart one of the most underrated and complex architecture on the internet, P2P and WebRTC. This is part of our new high-level series on system design, where we are aiming to give you the architectural big picture without the fluff. If you find these dives helpful, please hit that like button, share this video, and subscribe. It really helps the channel. For the full article and diagram, check our companion site, and this is available on these two pages. Um, this is actually GitHub pages. The link will be in the description. Um, in addition, there is another site which is so you can actually view here. This site is actually a work in progress. So if you want to take a look at that, some of the articles will be coming as we continue with our progress on these sites. Okay. Um, Coming back to the videos here. So this is part, as I mentioned earlier, this is part of our high level system design concepts. So we are keeping these videos very concise to respect your time. But if you want a dedicated session on any specific concept like DHT math or signaling state machines, let us know in the comments. We read all the comments and we'll make sure that okay, your video for the dedicated topic is actually created and we hand it over. Now let's get started with this video. Every networking decision now comes down to a trade-off between the scale and control. In a standard client-server model, the central server is the source of truth, but it is also the ultimate bottleneck and single point of failure. As you scale, your bandwidth costs grow exponentially. Peer-to-peer or P2P flips this. Every node is both a client and a server. The network becomes self-healing, and critically, we use P2P when the center around cannot hold the bandwidth, like for 4K video calling or massive file distribution. But how do you find a needle in a global haystack without a central directory? That's the job of the DHT engine. Instead of asking a server, where is this file? Nodes makes XOR distance math. Every node and piece of data has a 160-bit ID. The distance isn't geographical, it's a mathematical relationship between bits. This ensures you can locate any peer or file in olog and hops, meaning even with millions of users, you're only ever a few jumps away from your target. Even if you find a peer, there's a physical roadblock, network address translation or NAT. Most devices live in private networks with hidden IP addresses. While full cone NATs are easy to bypass, Symmetric NAT is the senior engineer's nightmare. It creates a unique mapping for every single destination, making traditional hole punching mathematically impossible without a relay. Understanding which NAT your users are behind is the first step in building a reliable P2P system. To get through these NAT firewalls, we use a hack called UDP hole punching. Both Alice and Bob connect to a rendezvous server to learn each other's public IPs. When they both fire outbound UDP packets at each other simultaneously, this tricks their respective firewalls into creating temporary holes for incoming traffic. The precise timing here is the critical path. If one side fires too late, the incoming packet is rejected as unsolicited traffic. To navigate these connections, we use two types of server, STUN and turn. Stun is your public mirror. It's cheap, fast, and simply tells you what your public IP is. It works for about 80% of the internet connections. But there is a symmetric NAT blocks your path, you need turn. Turn is a relay fallback. It is expensive and high latency because all the media flows through it. A pro tip, monitor your turn usage closely, or your cloud bill will end up your startup before you even launch. The orchestrator that manages all these possibilities is the ICE algorithm, Interactive Connectivity Establishment. ICE doesn't just pick a path, it gathers every possible candidate, local IPs, turn reflexive IP, and turn relays. It then systematically tests every pair to find the one that works with the lowest possible latency. ICE ensures that a local LAN connection is always prioritized over a public relay. keeping your performance as much high as possible. Now, WebRTC isn't actually one protocol. It's a Frankenstein monster of existing IETF standard like ICE, DTLS, and SRTP, all wired natively into your browser. This means you don't need plugins for real-time video. When debugging the WebRTC, your first task is to isolate the layer of failure. Is it a transport failure in ICE, a security mismatch in the DTLS handshake, or a simple application state error? Isolate the engine block to fix the bug. Here is the signaling paradox. You cannot negotiate a P2P connection without first having a connection. WebRTC deliberately omits the signaling standard. Before the P2P pipe can open, peers must exchange blueprints called session description protocols through an out-of-band third party. You have to build the state machine yourself using WebSockets or SSE. WebRTC handles the media. We handle the handshake logic. At the application layer, we are working with three core APIs. Get user media captures the hardware, your camera and mic. RTC peer connection is the engine that manages the ICE and security. And then there is the RTC data channel, the secret weapon. It uses the HTTP protocol, which you can configure to be reliable for file transfer or unreliable for things like multiplayer gaming position updates where speed matters more than every single packet arriving. Why do we race on UDP instead of TCP? Because the head of line blocking. TCP is a slow truck. If one box falls out, the whole highway stops until it is replaced. In real-time audio, a packet arriving 200 milliseconds late is worthless. It just causes a stutter. UDP is a sports car. It's fire and forget. If a packet is lost, the codec prefers to fill the gap with comfort noise rather than wait for the retransmission that would destroy the latency of live conversation. Security is baked in via secret security armor. We use DTLS to establish shared encryption keys over UDP and SRTP to encrypt every single media packet. To defeat man-in-the-middle attacks, we use SDP fingerprinting. By exchanging a certificate hash through your secure signaling server before the P2P connection starts, the browser will instantly reject any intercepted certificate that doesn't perfectly match that pre-shared key. If you're moving to production, memorize this diagnostic matrix. I've seen these three bugs take down entire system. First, forgetting trickle ice. Waiting for all candidates to resolve before sending an offer adds second to the connection time. Second, ignoring turn fallbacks. Testing on a local LAN always works, but production will drop 15% of users without relays. Finally, signaling state collisions. If both peers call at the exact same millisecond, your state machine will crash without a polite glare handling pattern. This is a complete synthesis. To click call, you capture local media, use WebSockets to exchange HTTP blueprints, discover network paths via stern or turn, perform a DTLS key exchange, and finally, flow encrypted SRTP media through the P2P pipe. Every layer operates independently, but failing at any single point breaks the entire chain. This is the anatomy of a modern real-time connection. To wrap up, here is the system design cheat sheet. Remember, stern is a mirror, turn is a relay, and UDP is the only way to beat head-of-line blocking. Now, here's a question for the community. Have you ever worked on a P2P system that suffered from symmetric NAT issues? And did you find a way to avoid the high cost of turn servers? Let us know in the comments below. If you enjoyed this video or this episode, please like, share, and subscribe to CSEI Think Tank Learn, and do explore the other topics on the system design essential as well. And thanks for watching, and I'll see you in the next one.